All right. Hello once again. All right, it's been a while, not been on the channel. So I thought maybe I should do one video and remind you that I'm still there. It's just that the busyness of life that keeps us away from participating or continuing with the program. However, the opportunity that I get, I'll be sending through some videos. So today I want us to look at chemical equilibrium, but I'll be focusing on questions. Maybe I'll also be addressing certain concepts there. So in chemical equilibrium, having a question from the year 2014, February, March, that is DBE, Department of Basic Education. So I would like us to go through that question and get to interact with it and see how best we can respond to the question. All right. So here's the question. It says that the reaction of methane gas, CH4, with steam, H2O, produces hydrogen gas. The equation for the reaction is shown below. So we see CH4 as a gas plus 2H2O as a gas, and giving us CO2 as a gas plus 4H2 as a gas. All right, before I even go further, I want us to look at this. There's a double arrow there, which is informing us of something, to say there's one arrow pointing to the right and one arrow pointing to the left. So this tells us the reaction is reversible. So when a reaction is reversible, it implies that the reactants form product, and product can be changed back into the reactants. All right. And again, we can see that our equation, our chemical equation, is having same states of phases, the gas throughout. Such equations, we call them homogeneous reaction. So homogeneous reaction will be those reactions having the same phases. Right. So the reaction is reversible and it's homogeneous. So 7.1 then says, briefly explain why carbon dioxide gas may be harmful to the environment. So carbon dioxide is a gas that contributes to greenhouse gases, which then leads to global warming, and which may also lead to climate change, and other factors that you can add. It's air pollution, Right. That is, you can even search for more on the internet to get the insight of how carbon dioxide is affecting the environment, and you can even further get about the health, or how does it impact us as human. Obviously, it has some good benefits as well, but in this case, we had to just to focus on the negative impact of this carbon dioxide. So initially, 1 mole of methane and 2 mole of steam are sealed in a 5.0 dm cubed or decimeter cubed container. So I'm interested in the term sealed there. The term sealed is informing us of a system that we are dealing with. So it's a closed system. So if you're looking at a closed system and the reaction is reversible, those two conditions are conditions for equilibrium. For us to be able to reach equilibrium, or to talk about equilibrium, the reaction must be reversible and the system must be closed. So when equilibrium is established or reached at temperature T1, the mixture contains, so at equilibrium, this is what we have of carbon dioxide gas. So this is how much was produced, how much was formed at equilibrium. Oh, because since carbon dioxide is a product, therefore it is being formed. So 7.2 is asking us to define the term chemical equilibrium. So chemical equilibrium will be a dynamic equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. Please make sure when you state this definition not to forget the rate. Once you miss that out, it will be incorrect. If it was me marking you, I would definitely give you a 0 if those terms are not there. All right. Let us look at 7.3 rather. Seven point three is asking us to calculate the equilibrium constant Kc at T1. So we'll discuss in case that the temperature changes, how does that influence the Kc value? So you can even see the number of marks there. So that means there's a number of calculations or steps that we need to do in order to get the value of Kc. And also I want us to touch on the significance of that value. All right. Have it this side. So I'm gonna have, for me to calculate my Kc, I will have to talk about the, okay, I call it the rice table or rices, because I'm going to be using Ri. Okay, let me start with the table first. So we have ratio, we have initial in moles, we have, what is that? Change in moles again. We have equilibrium, and note that you can do this using concentration throughout. Concentration at equilibrium in C is equals to N over V, which is measured in moles per dm cubed. Take me some time to deal with this one. Okay. Okay. There we go. It's coming all right. All right. So we have our CH4 reacting with two waters, giving us okay, that's fine. So I'm not going to include it here. So let me just get rid of it. We're going to go back to our reaction here. I want us to look at the moles. There is 1, there is 2, there is 1, there is 4. So that will be our ratios. So our ratios will therefore be 1, 2, 1, 4. So those are the ratios. And I want us to state something here. Under change, you may write the following. We use ratios here. Okay? And here, that's where substances are being used, substances are being formed. All right? All right, so initially, what are they saying? There is 1 mole of methane. Remember, I said my table will be in terms of mole, and there's 2 moles of, what is that again? Water, or the steam. And initially, products are not yet formed. So with that, what did they say again? They said at equilibrium, the number of moles of carbon dioxide, remember carbon dioxide, it's here, CO2. And this one is H2O, this one is CH4. And that will be the hydrogen gas. All right, so carbon dioxide has 0.3 mole. 0.3 mole. So if that is 0.3 mole, we are able to find the difference, which is the change. So final at equilibrium, what was formed or left, subtracting what was there initially. So that will be 0.3. All right. So change, remember I said, that's where we use ratios. That's where we use ratios. So let us look at now the ratio. Let me start with the 1-to-1. 1-to-1 means that the ratio are equal. So therefore, the number of moles will also be equal. If I look at 1:2, that means I must double the number. That will be 0.6. 0.6, double the number, that will be 1.2. Or you can simply say, if you are looking for this, you would say 1 divided by 1 times this. You're going to get that. If you're looking for this, you say 2 divided by 1 times this, which gives you that. If you're looking for this, it's 4 divided by 1 times this, which gives you that. So it's mole ratio. Now, I want us to also state the following. If it's a reactant, it means that it gets used up. So I'm going to say minus, and all the products are being formed. So I'm going to say plus. So I'm just going to add the numbers going down. As I add the numbers going down, what's going to happen? I'm going to be left with 0.7, and here it's 1.4, and here it's 1.2 if you add the numbers going down. Note, the minuses, I use them because I want to know how much is left after so much has been used. So now I have the number of moles at equilibrium. What is left of me is to calculate the concentration at equilibrium. So this is going to be 0.7, you divide by the volume 5, 1.4, you divide by 5, 0.3, you divide by 5, 1.2, you divide by 5, just like that. So grab your calculator and tell us what would the value be. So this will give us 0.14, and the other one, 1.4 divided by 5 would give us 0.228, and this one here, 0.3 divided by 5, that will give us 0.006, and 1.2 will give us 0.24. So these are concentration at equilibrium. So now the Kc expression that we must do is dependent upon the equation. There is no specific formula that we can say, okay, this is the formula to calculate Kc. It depends on the equation that is provided to us. So Kc is equals to the concentration. Let's see the C, carbon dioxide. What's the coefficient? It's 1. So H2, and the stoichiometric value there, it's 4. And concentration of CH4, exponent 1, and we have the waters. So H2O to the power what? 2. So with that, we are going to say 0 point, let's substitute quickly. So it's going to be 0.06 multiplied by 0.24 to the power 4 divided by that is 0.14 and that we put in 0.28, then to the power 2. Then what answer are you going to get there? Let's quickly work it out. So that's going to be 0.06 okay, there's no square there. Then there's 0.24 power 4. Then we have 0.14 in brackets and 0.28 in a square root, which gives me 0.018, in which we are informed to round off our answer to 2 decimal places. So that will be the value there. Alright, so we have our Kc value now. Since we have our Kc value, let us find, let's proceed with the question, or we need to explain what is the significance of this value. Note that if the Kc value is less than 1, the implication is that more reactants are formed than the product. And we can also add that when Kc is less than 1, a reverse reaction is favored. So maybe this may be of help to answer the next question. Another point is when Kc is greater than 1, it implies that more products are formed. And that means forward reaction is favored. Now, let us look at 7.4. 7.4, it says that a new equilibrium is established. So the disturbance there was at temperature, as to say, right? A new equilibrium is now established at a higher temperature, T2. So the key word there would be higher temperature. What did they do to the temperature? They have increased it. So T2 has a higher temperature than T1. So a higher temperature is associated to endothermic reaction. So we can see there a higher temperature favors an endothermic reaction. So what happens after? The value of the equilibrium constant Kc at this new temperature, it is now 0.01. What happened? The Kc value at T2 is less than that of the Kc value at T1. So we are observing a decrease in the Kc value. As we increase the temperature, the Kc value decreases. So I want us to look at the points that I just raised after the calculations and what I said about an increase in temperature. So increase in temperature Okay, let's go back. So the question is asking, before I could rush to answering the question is asking, is this reaction exothermic or endothermic? And it must use the principle of Le Chatelier and explain the answer that we have chosen. So we must use Le Chatelier's principle and the value of Kc at T1 and at T2 to explain these answers. Okay, for us to be able to respond to that, I just indicated to you that the Kc value is lower than that, or Kc value at T2 is lower than that at T1. And we just mentioned that when the Kc value is less than 1, it favors the reverse reaction. So this then informs us that the Kc value indicates a reverse reaction being favored, which means there is more reactants that are formed than the products. So increase in temperature favors what do you call this? The endothermic reaction. So we can say the reverse reaction is what? It's endothermic. So forward reaction would therefore be exothermic. So number one, forward reaction is exothermic. So when they ask this question, they are asking for the forward reaction. So the forward reaction is exothermic reaction. But why is then what we have? Why is it so? The points that we have raised are the responses or answers to the question, to the reason, or to okay. So the points that we have raised, they are reasons why we chose forward reaction as being exothermic. So in that case, we would say, what do we observe? We observe that an increase in temperature shows a decrease in the Kc value. And we can say, and a Kc value that is less than 1, note it further decrease. Remember, at T2, it further decrease. That's what we are observing. So that means reverse reaction is favored. And another thing that we need to mention is that increase in temperature favors endothermic reaction. So what does it tell us about the reverse reaction? So reverse reaction is endothermic. So that will be your bullet points that you need to consider when explaining 7.4. So I hope this made sense. Yeah, I hope it made sense. So the forward reaction is exothermic. We observe a Kc value decreasing, which means that there are more reactants being formed than the products. So we can therefore say that the reverse reaction is favored, and again an increase in temperature favors endothermic reaction. That means the reverse reaction is endothermic. That's why the forward reaction is what? Is exothermic. I hope this made sense. If there are something that I might have missed, you can share it on the comment section so that I may consider it in the next video or to touch on it, or any suggestions that you have, you can add onto them. And okay, so just not to forget something. When applying the Kc, or when you are writing the Kc expression, the only states that you look at are the gases and aqueous solution. If it's a solid and a liquid, we do not show them on the Kc expression, as they are regarded as having a concentration of 1 mole per dm, 1 mole per dm cubed at equilibrium. So we do not consider it. Right, thank you for that, for watching. And I hope it will help in terms of looking at other questions that are related, especially with temperature increasing and decreasing, and using Le Chatelier's principle to explain that concept. So we'll look at some questions where we may define Le Chatelier's principle, which talks about the disturbance of a system and the system now reinstating a new equilibrium by favoring that reaction that will oppose the change that has happened. So we'll look at some of the questions, but I thank you for watching. So I hope you enjoy and you improve on the subject matter. Thank you so much.